Triangle wave generator. Triangle wave consists of a non-inverting Schmitt trigger feeding into a ramp generator, which feeds back to the non-inverting Schmitt trigger. The Schmitt trigger will be producing a square wave of amplitude 13 volts, and the ramp generator is going to be producing the triangle wave output, the amplitude of that being set by the thresholds for the Schmitt trigger. There's a recap of the circuits then. So the non-inverting Schmitt trigger, we've got switching voltages set by this formula, set by the resistor ratios. And have a look at the graph. When if Vin is negative, then Vout is going to be negative. If we bring Vin above the positive switching threshold, then Vout switches to plus 13 volts. We then have to bring it below the negative switching voltage to make it switch back to minus 13 volts. Ramp generator. This is the formula for the ramp generator. If Vin is positive, then it's going to be ramping down, as this shows. So Vn is positive, it ramps in the downwards direction, and the gradient delta V out over delta T is given by minus Vn over Rc. This is an example, well, this is the circuit, so I'm just going to talk how it operates. So let's assume to start with we've got plus 13 volts here and we've got 0 volts to start with. So what's going to happen is that because this is positive, the triangle wave is going to be falling downwards, so the ramp generator output would fall down at a steady rate given by these values here. So we've got Vn, which is 13 volts from the Schmitt output. So you can see this falls down. And it's going to fall down until it reaches the negative switching threshold, at which point it's going to make the output of the Schmitt, so square wave, will saturate at minus 13 volts. Now because of that, the triangle wave is now going to rise because we've got a negative voltage going in, which means it's going to rise upwards, and it will rise up at a steady rate until it reaches the positive switching voltage, and it's going to cause the output of the Schmitt to go to plus 13 volts again. And then we just go around this loop again and again and again, endlessly. So triangle wave is going to fall down until it reaches the switching voltage, then it's going to cause the square wave to change to minus 13 volts. So let's put some numbers into it. So to start with, first thing we can calculate is the switching thresholds using these components here. So it's going to be 13 volts multiplied by, we've got the 10k divided by the 26k, and this comes out as 5 volts. And from this we know, therefore, that we're going to get 5 volt amplitude on the triangle wave. So when the triangle wave reaches 5 volts, it will cause the Schmitt to switch. Looking at triangle wave itself, we can work out the gradient of this, putting the values in. So we've got 130k and we've got 5 nanofarads. So we're going to get a ramp of 20,000 volts per second as a gradient. Now, in one complete cycle of this, to go from a start position back to that same start position, it's going to V out. The triangle wave is going to change by 4 times the switching voltage. That's 1 change, 2, 3, 4 changes. So the total change in V out is going to be 4 times the switching voltage in one period. So delta V out over delta T, 4 times the switching voltage divided by the period. And it comes out as Vn over Rc from this formula here. So plug in the numbers that we've got. So it's 4 lots of 5 volts for the switching thresholds divided by the period, and that's Vn over Rc as we got from here. Rearrange this to get the period, and the period comes out in this case to be 1 millisecond, which means that we've got a frequency of 1 kilohertz. So in short, in summary, with these particular values, we've now worked out that we've got a peak of 5 volts for the triangle wave and a frequency of 1 kilohertz.